Hello my dear students, welcome to the next lecture in analog electronics. In this lecture we are going to discuss metal oxide semiconductor field effect transistor, its construction, working and characteristics. So these are how MOSFETs are classified into based on its construction and working. The first one is enhancement mode and the other one is depletion mode MOSFET. And as just like any FET or any semiconductor devices, here also there are P and N channel types. So depending on the substrate, these will be changing, that is P type and N type, that is P channel and N channel MOSFETs. So we are going to discuss enhancement mode MOSFETs. Before we discuss the construction, let us go through the symbols of N channel MOSFET. In enhancement mode, this is the symbol. Please note the difference between the symbol for enhancement mode and depletion mode. In depletion mode, you can see this is continuous, whereas in enhancement mode, you can see this is in this format, that is splitted. This simply means that in depletion mode, there is a channel which is present in the substrate of the semiconductor device, which is in the construction wise itself, that channel is there in the depletion mode. We are not going to discuss the construction and working of depletion mode, but in enhancement mode there is no continuous channel present. It is produced by applying a voltage at the terminals of gate and source in enhancement mode MOSFET. We will see that in detail. If it is P channel, the difference will be the direction of arrow, as you can see here. In P channel MOSFET, you can see the arrow is pointing out from this left to right. If it is depletion mode also, it is the same, and the only difference is between enhancement and depletion is that it is continuous for depletion mode, showing that there is a channel inherently present, and it is discontinuous for enhancement mode. Now, let us discuss the constructional features of an enhancement type MOSFET. As you can see here, there is a slab of P material. This is the P substrate, as you call it, formed from silicon base, and it is the substrate. Now, in some cases, the substrate is internally connected to the source. That is, this substrate terminal is internally connected to the source. The source and drain terminals are connected through these metallic contacts. You can see drain is connected to this N-type material through this metallic contact. And the gate is also connected to a metal surface. So here source is also connected like this to the N-doped region, which is embedded in the P substrate. So this N region is embedded here, and drain and source are connected to these two regions. There is no connection between these two, as you can see. And this gate is isolated from the region between this drain and source using a dielectric, which is silicon dioxide layer. As you can see, this is the silicon dioxide layer. It is marked here, silicon dioxide layer. Now, you can see that there is no direct electric connection between the gate and the P substrate. There is a dielectric in between them. You can see this. There is no direct connection between the gate metallic contact and the P substrate. Now, it is this insulating layer of SiO2 which is giving the high input impedance to this MOSFET. Okay. Now, let us discuss the working of an enhancement type MOSFET. So, what happens in this condition? The applied voltage across gate to source is 0. That is, VGS is 0. If VGS is 0, when a voltage is applied between this drain terminal and the source terminal, will a current flow from the drain to source? Keeping VGS 0, just like we discussed the FET, if a voltage is applied between the drain and source, will a current ID flow through this drain to the source? The answer is no, because in an enhancement MOSFET there is no channel, there is no N material here which can cause a flow of charges from the source, electrons from source to drain, or current ID will not flow from the drain to source, even if VGS is 0 volt here. Okay. But in depletion, there is already an N channel here. That is the difference between depletion and enhancement type MOSFET. Okay. Now, what will happen if you give some positive voltage? What will happen? If you give some positive voltage here, something is going to happen with respect to this MOSFET. Also note that at VGS equal to 0, with this VDS applied like this, some positive voltage is applied across the drain to source, there will be two reverse biased PN junctions here. This one PN junction and this PN junction. There will be two reverse biased PN junction between the N dot regions and the P substrate. So that is explained here. In this slide explains the working when VGS equal to 0. Now, VDS and VGS both are greater than 0. What will happen? So, as I showed you, there is a voltage connected between the drain and source, and the substrate terminal, this SS terminal is shorted with the source. So, these two are shorted together, and a voltage is applied between the drain and source, that is VDS, and VGS is made positive. It is made greater than 0. What will happen? So, the drain and gate is at a positive potential with respect to the source terminal. Drain is at a positive potential because of this source, and gate is at a positive potential with respect to source because of this VGS. Okay. Now, since this is at a positive potential, of course, there is no current flowing through the gate, isn't it? So, Ig is 0. The positive potential at this will try to attract the electrons to this side, and the holes will be repelled. So, in the P substrate, the holes along this edge of this SiO2 layer will leave this area and enter the deeper regions of the P substrate, and electrons will accumulate along here, forming a channel between the drain and source. So, the depletion region near the SiO2 insulating layer thus become void of holes. There won't be any holes here in this region. Okay. Now, as you can see, the electrons have accumulated in this region near the surface of the SiO2 layer. So, the SiO2 layer and its insulating qualities will prevent the negative carriers from being absorbed at the gate terminals. That is, these carriers, these electrons won't be absorbed by the gate terminal, as this dielectric is there in between. This insulating layer is there in between. Now, what happens as VGS increases in magnitude? If VGS magnitude is increased, this is increased. Okay, this was 0. Now we have applied a potential, and now we are trying to increase this VGS. What happens? If VGS increases, the electron concentration here will also increase. Until when? What will happen? This induced N-type region will support a current flow between the drain and source. Okay, so the level of VGS that results in a significant increase in the drain current through this channel. That is, this VGS should be increased to a level. So, this VGS has to be increased, and that has to be increased to a level known as threshold voltage, which is represented by Vt, or there is another representation, that is VGS threshold. These two are the representations for the threshold voltage. As VGS reaches this threshold value, what will happen? There will be an increase in the drain current which is flowing from the drain to source through this channel. Alright? Okay. So that is explained in this these slides. You increase VGS. Now, why this MOSFET is known as enhancement type MOSFET? Because the channel is non-existent actually. There is no channel when there is no voltage applied to the device. But when VGS is increased by the application of a positive gate to source voltage, what has happened? There is an enhancement. The channel is enhanced. That is why it is known as enhancement type MOSFET. Now, when VGS is greater than V threshold, what will happen? When VGS is made greater than V threshold, if we increase the level of VDS, okay, we make VGS at a value greater than V threshold and we maintain this VGS constant at that value. Suppose the threshold voltage is 2 volt. We make the VGS greater than V threshold. We make it 3 volt, say, and you maintain it at constant. This VGS is then maintained constant. Okay. Then if you increase the level of VDS, what will happen? The drain current will again increase and it will reach saturation level as it occurred for a JFET. I hope you remember the JFET Cara. You saw that the beyond the pinch off voltage, the ID was saturating at a particular level. Similar to that, the ID will increase and then it will reach a saturation level for this particular MOSFET also. So let's see that. So this is the change in channel and depletion region with increasing level of VDS for a fixed value of VGS. That is, now VGS is fixed at a particular value and you are increasing the value of VDS. What is happening now? Suppose this VGS is fixed at a value of 8 volt. Okay? And VDS is increased. Now you are starting to increase this VDS from say 2 volt to 5 volt. Okay? What will happen to the voltage VDG? What is VDG? The drain to gate voltage. What is VDG? VDG is VDS minus VGS. So what is VDS? Initially it is 2 volt and then VGS is 8 volt. It is constant. So it is minus 6 volt. And now you have increased VDS to another value. So this is VDG1. Now what is VDG2? It is, you have increased this to 5 volt, VDS to 5 volt, maintaining VGS constant at 8 volt. Now it is minus 3 volt. So you can see this VD is increasing from minus 6 volt to 3 volt. Or the inverse, if you take this VGD is changing from 6 volt to 3 volt. Or the gate will become less and less positive with respect to the drain. So this reduction in gate to drain voltage will reduce the attractive forces for these free carriers or electrons in this region. Okay, these electrons are there in the induced channel. So this will cause a reduction in the effective channel width. So the channel width reduction will be in this manner itself, as we have discussed the resistance of the channel. From the source to drain, it will become narrower. Okay, so the channel will be reduced to a point which is pinch off. So you can incorporate the idea of a JFET. So it will reach pinch off and the saturation condition will be established similar to a JFET. So here the channel width reduction is caused by this reduction in gate to drain voltage, which is reducing the attractive forces for the electrons to the gate. That is, this attractive force is reduced and that is how the channel width is reduced. Okay. So similar to JFET, if there is any further, this is happening as VDS is increased, keeping VGS constant. If you further increase VDS at a fixed value of VGS, then the saturation level of ID will not be affected until breakdown. We will see the characteristics. So these slides are explaining the working which I just discussed with you. Okay, now let's see the characteristics. So here you can see for a fixed value of VT, we explain for VGS is equal to 8 volt. Higher the level of VGS, the greater is the saturation level for the VDS. That is, this is the saturation level for VDS. This point is the saturation level for VDS. So for VT equal to 2 volt, what is VDS set? For VGS is equal to 8 volt. 8 volt minus 2 volt, it is 6 volt. You can see that marked here. This is 6 volt. Okay. So this is at 6 volt. But as you decrease VGS, what happens? As it is 7 volt, you see it is further decreasing, and this VDS sat is decreasing. So this is decreasing and following this is the locus. Okay. For values of VGS less than the threshold level. Now as VGS reaches the threshold level, you see what happens. this as VGS is equal to V threshold. That is, threshold value is 2 volt for this particular device, and as VGS reaches equal to V threshold, what is VDS at? Is 0. VGS minus VT is 0. Or you can say that ID will decrease from this 10 milliampere saturation value, it is coming to 0 as VGS is equal to VT. Okay, so the enhanced current is 0 as VGS is equal to VT and or below VT. That we know, we have discussed. There won't be any channel formation if the VGS is less than V threshold. Now you, as you move up again from VGS is equal to VT, from VGS is equal to VT, or you make it greater than VT. As you move up, you can see that the saturation level of ID is also increasing. ID is increasing. For VGS equal to 4, it is here 5, 6, 7, 8. It is coming to 10 milliampere. From 0 to 10 milliampere. The spacing between the levels of VGS also, that is also decreasing as VGS is decreased. Okay, the spacing between VGS is also decreased. Okay, for then we have a relation here. For the levels of VGS greater than VT, the drain current is related to the gate to source voltage by a non-linear relationship. We'll see that equation. This is the equation for drain current when the gate to source gate to source voltage for VGS greater than VT. VGS has to be greater than VT for the drain current to follow this relation with VGS. Okay, this is a non-linear relation. So it is a square term that results in the non-linear relationship between ID and VGS. So this, what is the relation between ID and VGS? What does it mean? ID is the output and VGS is the input. So it is nothing but the transfer characteristics of this MOSFET. Now at VGS is equal to VT, this square term will be 0 and ID is 0 milliampere. We discussed that. Or for VGS less than VT, this ID will remain 0, less than or equal to VT. You have seen a K term here. We saw this K term when we saw the characteristics as well. I have written a value for K here. K is 0.278 into 10 raised to minus 3. I hope you can see this value. We'll see how we got a value for this particular device. This Kara is for a particular device. We'll see. So this K term is a constant, that is a function of the construction of the device. Now, how can you find K? This K can be determined by this relation ID on by VGS on minus VT the whole square, where ID on and VGS on are the values for each at a particular point on the characteristics of the device. You can find these points on the characteristics. So if you take a point for this ID on equal to 10 milliampere, we know that VGS is 8 volt from the Kara. So you can calculate K. This will be ID on 10 milliampere by VGS on, for that 10 milliampere is 8 minus 2, and you get a value 0.278 into 10 raised to minus 3 ampere per volt square. So this K will remain the same. You can prove that for yourself taking any other points. Say on the Kara, if you have 4 volt, say VGS is equal to 4 volt. Okay, if you substitute it here with this K value, you will get ID as the same. If you substitute in the expression with the same K value, you will get it as this for this particular. I hope you can. Okay, so for this K, you will get it in the range 1.1 milliampere or so. You can do it that for you and prove it for yourself, substituting the same K value in the expression which we just discussed, that is ID on by VGS on minus VT the whole square. Okay, so this is the transfer characteristics. So you know, this is the nonlinear relationship based on which we are plotting the transfer characteristics. Similar to a FET, you can plot it here. As VGS is increased beyond VT, the drain current ID will begin to flow at an increased rate. That is, this equation is giving that relation. So when VGS is equal to VT, this ID is 0. You can see that here. When VGS is equal to VT, ID is 0. And this is the point for VGS is equal to 8 volt, that is ID is 10 milliampere, and like that you mark the points and plot the transfer characteristics. Now I am giving you a homework. You can refer Boylsted. You can plot the transfer characteristics if the K and Vt values are given. You can refer the book and do it for yourself. The procedure to plot the transfer characteristics with a given value of K and Vt. So with this I am ending a discussion on MOSFET enhancement mode MOSFET, N channel MOSFET. P channel MOSFET will be the complementary of what we have discussed so far for the N channel enhancement mode MOSFET. Thank you.